Hello everyone. Welcome to this virtual classroom on the unit namely Nonlinear Mechanics and Chaos. So far we have considered and studied mechanics, but it was dealing with the linear systems. When do we call any system to be linear? The system that can be represented by equations of lines is considered as a linear system. For example, this is a linear equation of n variables. Consider a simple equation involving only two variables. Y is equal to 3x. It is an equation of line. It represents a system where dependent variable y varies linearly with an independent variable x. If along with y is equal to 3x, x is equal to 3y is also given, the solution of the system is the point of intersection of two lines, and we can see from the figure that it is 0, 0. That is, origin is the solution of the above system. We can also recall linear system of differential equations representing damped oscillator. md square x by dt square equal to minus kx minus c into dx by dt, where left hand side represents net force, minus kx is restoring force, and minus c into dx by dt is the damping force. We can always convert this equation to dv by dt equal to minus kx minus c into dx by dt. Using definition of velocity, that is dx by dt equal to v. This is a linear equation. We make certain approximations so that such equation can be solved exactly and analytically. Approximations are like pendulum with the point mass or massless string or small angular displacement or even absence of air resistance, etc. For example, the restoring force is considered to be linear here. That is, F is equal to minus kx. It is assumed that F is linearly proportional to x. In fact, almost all systems in nature are nonlinear. That is, they may involve higher powers of variable. For example, when restoring force f of x, when expressed like this, that is functions of even higher powers of x, such system becomes complicated and the equations are no longer easy to solve analytically. Hence, they are solved numerically. The question is, why are nonlinear systems so much harder to analyze than the linear ones? The reason is simple. Linear systems can be broken down into parts and then they can be solved and recombined to get the answer. But nature doesn't act this way. Most of the everyday life is nonlinear and the principle of superposition fails spectacularly. For example, if you are listening to two of your favorite songs simultaneously, your happiness doesn't get doubled. Although dynamics is an interdisciplinary subject, it was originally a branch of physics. We all know the subject began with the invention of differential equations and discovery of laws of motion by Newton in 1600s. Newton gave inverse square law of gravitation and explained Kepler's laws of planetary motion. Up to 1800s, only Newtonian mechanics prevailed. Though scientists were working on nonlinear systems also, they were using numerical methods and had limitations. It was Poincaré, a French scientist, who developed a powerful geometric approach for analyzing complicated questions. He was the first person to glimpse the possibility of chaos. A mathematician and physicist, Poincaré made many original fundamental contributions to pure and applied mathematics, mathematical physics, and celestial mechanics. In his research on the three-body problem, Poincaré became the first person to discover a chaotic deterministic system, which laid the foundations of modern chaos theory. He is also considered to be one of the founder of the field of topology. In this unit, we are going to discuss what is chaos. Chaos brings the loss of predictability even when the laws of nature that are governing a system's behavior are deterministic. But up to 1950, chaos remained as a nightmare. Dynamics largely concerned with nonlinear oscillations and the applications of nonlinear oscillators in physics and engineering. Radio, radar, phase locked loops, lasers, these are the technologies that got developed due to nonlinear oscillations studies. The invention of high-speed computer in 1950 was a turning point. At this point, we can look at Lorenz's discovery in 1963 and listen to an interesting story about it. With the advancement of fast computers, scientists came up with the mathematical models of complicated systems solving numerically. Edward Lorenz was also working on the most complicated phenomenon in the nature, that is, weather forecast. One fine day, he was working on his model. It was a simplistic model. It was displaying some features of real weather forecast. He fed into computer some initial values, say temperature, pressure, wind velocity, humidity, etc. The computer would solve the equations and predict the changing weather with respect to time. He got the printout. For some purpose, he wanted another run to see the changes in the weather in a particular time interval at greater length. He took a shortcut. Instead of whole run over, he started the program midway through. He typed the initial conditions and walked down the hall to get away from the noise and had a cup of coffee. And what he observed when he returned back changed the history, and a new science got developed. He observed, though the graphs in the two cases started off nearly the same, but rapidly diverged from each other with increasing time. There was neither any error in the program nor in the machine. When he realized the truth, he was also surprised. In the computer memory, the values were stored up to 6 decimal places. For example, 0.506127, sum of the value. In the printout, it came up to 3 decimal places to save the space, like 0.506. For the second run, Lorenz himself entered the initial values for that from the printout. Thus, by altering the initial values by a very small amount, that is, instead of 0.506127, he entered 0.506. So very small amount of difference is there in the initial values. But that led to the dramatically changed weather forecast. The resulting unpredictability despite the deterministic laws is called chaos. We know that in the system, all laws were properly entered in the program and they were determining the result. Lorenz's model of weather forecast displayed such chaos for the first time. It showed that the small change in one or more of the initial conditions could completely alter the system, and eventually the outcome becomes unpredictable. This discovery of Lorenz is known as considering the effect of very small changes in the initial conditions. It will not be an exaggeration if one says that a butterfly flapping its wing in Africa brings a hurricane in North America because of small changes in the temperature and pressure in the air due to flapping of its wings. hence the name butterfly effect. Knowing all this, we can define chaos as the unpredictability of the motion of the system associated with the sensitivity to the initial conditions is termed as chaos. In the next lecture, let us see one-dimensional anharmonic oscillator. Thank you.